Okay, welcome back, everybody, to the new year and your favorite class. Yes. Okay. So 4 o'clock, here we are. Class announcements. Oh, I got to share my screen. I didn't even share my screen with you guys. Oh, God, terrible. Okay, so obviously we'll continue our mass moment of inertia notes today. We're going to try to finish those up and a bunch of example problems today and some new material, so it'd be a good day. Homework number 3 was due today. That's area moments of inertia, not to be confused with mass moments of inertia, obviously. Due today, and I've posted a new homework number 4, which will be due a week from today, Tuesday, on mass moments of inertia. So you can tackle that after today's lecture. You should actually be able to do everything on there. So do that. That'll be due next Tuesday. This is all in preparation for your first exam for the class, which will take place next Thursday during the lecture period. So a little bit more information on that to come and how that's actually going to go, but more or less, the exam will take place virtually, so you'll take it at your place of residence or wherever you'd like to take the test. You can come here and take the test if you want, though I will not be here. The idea is you'll have the entire class period, so an hour and 50 minutes to do the test, and it'll be on everything that we've covered so far. I've posted practice problems for the test. I think there's like 12 or 13 practice problems, pretty good depth for those practice problems, alongside my fully handwritten solution for those practice problems. That took me a minute, so utilize it, please. The topics for the test will be friction, centroids, area moments of inertia, and mass moments of inertia. So everything through what will be the end of the lecture today. We'll start in on new material Thursday. That'll be on rectilinear motion. Finally, we'll get into some motion in this class. It's called dynamics. We haven't done any motion yet. Kind of funny. But we'll finally get into motion starting on Thursday, but you will not be responsible for anything related to rectilinear motion, which will start on Thursday. It'll only be friction, centroids, area, and mass moments of inertia. Cool? Okay. How you guys like this picture? I was telling the guys here in person, I took this picture while I was traveling between my fiance's house and my house. Took this picture in Ohio at a Phillips station. And this guy's representing Wisconsin quite well, if you can tell. So he's like pulling the gas, fill up to the other side of the car. It's like, oh my gosh. And then the best part, and I told these people in class, but the best part is the guy tells his wife to get into the car and put it into reverse so that he can like reach the gas filler thing to his car. Like, oh my God. You can see the lights of the car are on. She's like actively going in reverse right now. I was like, oh, you're going to run a vehicle while pumping gas into it. Like, that seems very safe. Like, I think that's the first thing they teach you when you fill up your car is like, don't have the car running, right? Like, oh my gosh, I could have died. Okay. Who's going to teach you triple integrals? Okay. Right. So there you go. Spatial reasoning is difficult. Not everyone cut out for engineering. Fortunately, all of you are. So that's good. Okay, let's pick up then where we left off, which is on mass moments of inertia. And I'm going to do a bit of a recap here since we've had a little bit of holiday hangover, I guess we could say. And we'll do a quick review here, especially since you guys were just working on area moments of inertia for your homework that I'm sure you all finished before today. But let's just do a quick review so we make sure that we know we're talking about mass moments of inertia today, not area moments of inertia and what the general differences are. All right, so let's just do a recap quick and pick up where we left off. Okay, the first thing we talked about when we talked about mass moments of inertia was the sort of analogy on what mass moment of inertia is, kind of in a physical sense. And the first thing I asked you when we introduced this particular topic was what is mass, and had some wide range of definitions, but generally if we think about like a linear sense of like what is mass, you think of pushing a crate along some slippery surface, all right, some frictionless surface. You're going to apply some force here, F. And this thing is going to accelerate to the right with some mass times acceleration. All right, so this gets you to think of your well known at this point Newton's second law, which is that force is equal to mass times acceleration. Or if you want to think of your definition of mass in this sort of analogous way, you would think that mass is equal to force divided by acceleration. And the idea here, the way that I wanted to frame this was you could think of mass as like the amount an object resists linear motion given some force applied to it, all right? So if we had a big, huge truck, we applied a certain force to it, it's not going to accelerate nearly the same amount as if you have a tiny little pebble and you apply that same force to it, right? So this is one way that you might want to think about mass. It's the resistance to acceleration given a certain applied force. And I motivated mass moment of inertia by saying that there's like an angular analogy to this mass idea, and that angular analogy is the mass moment of inertia, right? So with an angular analogy, you might have a box that's like resting on a frictionless surface. Now it's resting on a frictionless surface that's in the plane. And we apply some moment to this or some torque to this. Oh, that's terrible. All right, here apply some moment or some torque, however you want to think about it. And this guy is going to respond in a kinetic fashion, meaning like a moving with what we know is I alpha. And you just kind of have to take my word for this for now. We're going to dive in on this a little bit more later. But this is the sort of analogy to Newton's second law, which is F equals ma, but the angular analogy for this, which is that for an applied moment that you give to an object, it's going to have an angular acceleration, which is proportional to the mass moment of inertia, I. So we can sort of define these terms. Obviously here, this is your moment. This is angular acceleration. And this guy here obviously is your mass moment of inertia. Where this would have units of something like kilograms meters squared is common for SI unit, right? And you could rearrange this particular equation, much like we did for the linear equation, to get some idea or some feeling what this mass moment of inertia actually is. And it is the moment that you apply normalized by, sorry, not I, normalized by the angular acceleration. So the way you might want to think about this is the mass moment of inertia is the resistance of an object to angular acceleration given an applied torque. Okay? So if you have something with a very high mass moment of inertia and you torque that object, it will not spin very fast. If you have something with a low mass moment of inertia and you apply that same torque, it will spin very fast. All right, that's sort of the analogy that we want to sort of make here. Okay. So we went on to kind of define what this mass moment of inertia is, and the way that we did that was we looked at how much, what a mass moment of inertia is for a single particle. Okay, so for a single particle, we more or less looked at if we had an axis of rotation, let's call it AA prime, not to be confused with AA Ron, right? AA prime, and you've got some particle that's out in space. You call it DM, I guess, since we're going to talk about whole bodies in just a second. But let's say that you have some particle that exists out in space, and it has some mass m. And the distance that that particle has away from your axis of interest, let's call that the distance here r. Okay. And let's say we want to spin about AA prime. All right. We say that the mass moment inertia of particle about this axis AA prime is the following mathematically. It's the mass of that particle times the distance that that particle is away squared from that axis. So the farther and farther you get away from a particular axis that you are spinning about, the more difficult it becomes to spin about that axis with a square proportionality, right? So if it's twice as far away from that axis, it's 4 times as difficult to spin about that particular axis. So that was the general definition that we had. And we took this idea and we applied it to not just a single particle, but a full rigid body. So for a full body, we can assign differential mass dm, which is an infinitesimally small amount of mass at any one particular point in a body. And then we sum up all the contributions of all of those individual points, consider each one of those individual points distances away from our axis of interest. And we would say here that the area mass moment of inertia, I, is the integral on the mass of the distance of each particle squared multiplied by its individual mass component. So this was our sort of broadest definition for the mass moment of inertia of a full body. And I'll give this sort of a very light boxing, because this form is the most general form, but rarely used. Okay. All right. So this is nice, but usually we want to work in some standardized coordinate system. So we saw that in rectangular coordinates, you might have something that looks like this. If we say this is x, y, z, and you've got your object that exists here, pretend this is a 3-dimensional mechanics potato, my favorite kind of potato. UConn ain't got nothing on this, right? And you have some mass that exists out here, some differential mass, dm. Then you have to consider what is the distance that this differential mass dm is away from any of axis of interest that you care about. So if you're interested in, let's say, the area moment of inertia of this guy about the y-axis, then you care about the distance that this particular differential mass is away from that y-axis. Let's call this d sub y, the distance away from the y-axis, for instance. And if you understand your trigonometry well, you would understand that dy is just the square root of x squared plus z squared. Square root, right? So now when we go to our area moment of inertia equation for, let's say, iy, you have the integral on the mass of your distance that particular particle is away squared from that axis. So that would be this quantity here squared, which is just x squared plus z squared dm. So in rectangular coordinates, you saw something like this. The area moment of inertia can be defined using x and z coordinates. Area moment of inertia of x was the integral on the mass of y squared plus z squared dm. And the mass moment of inertia of z-axis would be the integral on the mass of x squared plus y squared with the same sort of analogy. All right, so we saw these as our sort of rectangular representation of the mass moment of inertia about these principal axes, which we're sort of all comfortable with, x, y, z, ABC, 1, 2, 3, Michael Jackson approved. All right, but we still have this hanging question of like, what is this integral dm? Like, what does this integral even mean? How do I integrate over the differential mass of a particular object? Well, we also had a way for tackling that. So what is mass integral? And we noticed for a homogeneous body, that is one with a constant density throughout, that the mass of an object would just be the density of that object multiplied by the volume of that object. Yes? We could take this idea and run with it in the differential form, meaning that the differential mass at any particular point inside of our body is just whatever the density of that body is multiplied by the differential volume at that particular location. So we wrote that as rho times dV. And this gave us sort of an idea or an inkling of what was coming next. And that is, we've done areal integrals in the past. Now we're going to do volume integrals. Volume integrals are triple integrals. And let's all have a good cry about that. Okay, crying time is over. Now we're actually going to do it, right? So this would be a triple integral. Right? Where if you're in rectangular components, or Cartesian as it's sometimes called, your differential volume element is going to be just something like dx, dy, dz. Or you could rearrange that any way you'd like, dx, dz, dy. Any sort of combination as you see fit, as you want to execute your integral from the inside out, can rearrange that as you please. Going to make life easier or harder for yourself doing that. All right, so we did an example where we looked at this triple integral with rectangular components. I'll remind you what that looked like. I'm not going to go through the whole example, but it was this example that looked something like this, where we had this rectangular prism. We were looking at defining the boundaries appropriately, going through the triple integration. We went through that whole thing. Kind of gave you the answers and asked you to maybe work through the integration yourself if you were feeling spicy. Okay. So that was our representation with rectangular coordinates. And then we also had a representation in cylindrical coordinates. And that is your dV is going to be r dr d theta dz, or whatever your longitudinal cylindrical axis is, where this z component is cylindrical axis. So if your x-axis is your cylindrical axis, it just gets replaced with the dx, right? And today we're going to see an example where we use these cylindrical components to do a triple integral to evaluate the mass moment of inertia of a right cone. All right, so this is about where we left off. We did an example, and now we're going to work through an example with cylindrical coordinates, because much more often, mass moments of inertia of objects in cylindrical coordinates are not well defined. And we have a lot of engineering application for cylindrically shaped objects. So we'll go through that example now, and I think it's important for you guys to know how to use cylindrical coordinates, especially for triple integrals, since you're kind of seeing these triple integrals, I think some of you for the first time. So let's try an example. So here we'll go through this example here. This is in your notes. I have uploaded the full solution of this to Canvas. If you'd like to take, I wrote Blackboard on here. I keep doing that. Like since we've used Blackboard so much, it's on Canvas. The full solution's on Canvas. We're gonna go through it now though, just because I want to talk about some things, and I think working through it together as a class is important. So, set up triple integrals to evaluate mass moment inertia for right circular cone. Give you a couple minutes to copy down, and then we'll work through it. I'm just going to change this. Blackboard. Okay. Canvas. All right, give you another second here, and then we'll work through it. You might also want to think about like what we're actually physically trying to do here. We want to calculate the mass moment of inertia of this object about the x-axis and about the y-axis. So what this physically means is we're trying to figure out how much this object would resist spinning about the x-axis given an applied torque, and also how much this object would resist spinning given a torque about the y-axis. So think about like taking this cone and spinning it around the y-axis. It's going to have a different resistance to an applied torque around the y-axis than it will about the x-axis. But the mass moment inertia about y and z will be the same. That's why we're not asking about z, because it's going to be the same. It's axisymmetric in the yz plane, right? Okay. So let's give this a run and see how we can do. All right. Be the mass moment of inertia about x and mass moment of inertia about y. Okay. I will say one more little caveat here. So we want to express in terms of the mass of the object. M and constants. So when you're talking about the mass moment of inertia of an object, usually that's going to involve the mass of that object times some sort of constants associated with the dimensions of that object. Remember, our units for mass moment of inertia are like mass times length squared. All right. So if we want to express our final result in terms of the mass of this object, then we should probably come up with some expression that is the mass of this object. All right. So let's do that. Let's calculate mass of object terms density and constants. You'll see why this is important later. If you remember our rectangular prism problem, you remember that we substituted in some constants for our mass at the very end to express our mass moment of inertia in terms of the mass of the object. We're going to do a similar thing here. All right. So volume of a right cone is, here's just 1/3 pi a squared h. You can look this up. So just think of a cylinder multiplied by 1/3. It's usually the easiest way for a cone. Pi squared a is the base times h, which is the height. For a cone, it's 1/3 of what would be the cylinder. So with constant density of rho, then my mass of my object is just rho v, which I'll say is 1/3 rho pi a squared h. Okay. After we work through our integration, we'll make a substitution at the very end, substituting what looks like this back for a mass. That way we can write our final result in terms of the mass of the object. Don't worry if that's not super clear right now, it will become clear. Okay, so now we're going to do our mass moment of inertia about the x-axis. It's this like cylindrical axis here, this x-axis. Okay. All right, our most general form is the integral on the mass of what is r squared Tm. Right? We know if we have like a homogeneous material, we're going to make that assumption here. This goes to the integral on the volume of r squared times rho dv. All right, where r is the distance from any differential element to our axis of interest, which is the x-axis in this particular case. All right. Now, we need to define our dv. And we sort of talked about defining the differential volume as dx, dy, dz, which is your sort of rectangular components. But in this situation, since we have an axisymmetric cone, it's probably easiest to work in cylindrical components, and I'll show you why that is in just a second. So we're going to use our cylindrical definition of the differential volume, which is r dr d theta. Here now we have to incorporate the longitudinal axis, which is not the z-axis as written previously, but here our cylindrical axis is the x-axis. So let's now really walk through what it is that we're sort of doing with this particular integral. All right, let's write it out fully here. So this integral on the volume, which will be a triple integral of what is r squared times rho r dr d theta dx. So we sort of had a conversation about double integrals before the break and a little bit about triple integrals. So let's actually like visualize this particular integration. So we're integrating from the inside out r theta x. Okay, so our first integration is with respect to r, second with respect to theta, and third with respect to x. So I go back up to my cone here and I think about just some random arbitrary volume element that might exist in this piece. Maybe let's draw it here as some volume element. Okay, sort of on the outer edge of this particular piece. The first thing I'm going to do is I'm going to integrate with respect to the variable r, meaning I'm going to expand this element, this volume element, along the r direction until I run into some boundaries. And so there are two ways that you could think about what boundaries you're going to run into for this particular cone, but you're going to integrate radially. And you're going to expand this guy here radially, regardless of where you are, to the boundaries. You may establish one of your boundaries as the center of the cone, or you may establish one of your boundaries as the sort of opposite, diameter of the cone. Either way is fine, you just have to know what you're doing. I think easiest is to sort of define my boundaries of my integration from the center of the cone, which is r equals 0, to the outer edge of the cone, which is here, the radius of the cone, which changes along the x direction. So the idea here is to define our integration appropriately, we need some function that defines what is the radius of this particular cone as we move along x. What I mean by that is, what is the radius of this cone as a function of x? Okay. Come back to that in just a second. Let's actually tackle that now. Okay, so here we'll note that the radius of my cone as a function of x, this is just going to follow slope-intercept form. So if I think about the equation of this particular line, I want to define the radius of this cone as a function of x. Well, this is just a slope-intercept form, where I know that this particular point has a height of a, and it has like a run of h. So this point here is h comma a, right? So if I wanted to define the radius of this cone at any particular point x, well, the slope of the line that defines this particular outer edge of the cone is the rise over the run. So it would be a over h times x. Is that clear? This helps me define the radius at any particular location x. All right, so this will help us define what is the boundary for our first portion of the integration. So I'm integrating from the inside of the cone, which is r equals 0, to the outer radial boundary of the cone, which is defined by the function a on h times x. All right, so those are my boundaries for this particular radial integral from the inside to the outside of the cone. All right. So that's kind of like the first step of this particular integration. Is like we're integrating this particular element to build what are like these long rectangles that exist between any particular boundary that exists at any location along this particular cone. So the first thing I'm doing is I'm making these like strips that exist between the inner edge and the outer edge of the cone, right? All right. Next, I'm going to integrate on theta. And so what I want to do here is I want to take this thin strip that I've basically made and integrate all its contribution around sort of the radial dimension or the theta dimension of any particular location. So what I'm doing here is I'm taking that thin strip that I've made from integrating between 0 and the outer radial distance, and I'm building for myself little plates that exist at this location by sweeping all of this area around. Okay, so that's what's happening with my second integration. So my boundaries on this particular integral are, I'm going one time around the circle. So from 0 to 2 pi or negative pi to pi or any sort of boundaries that get you a revolution of 2 pi. So integrating here on the theta variable, I'll go 0 to 2 pi. Okay. My last step of the integration is the x dimension. And that is more or less taking all of these plates that I've made and sort of adding them all up on my domain defined by x. So the boundaries here, adding all of these plates up that I've sort of created for myself by sort of sweeping each particular location will be from 0 to h. How are we doing with that? It's probably the most difficult part of this problem is setting up this cylindrical coordinate triple integral appropriately. Okay. So we can do a little bit of cleaning up on this guy. By sort of pulling this R together with the R from the differential volume contribution. Okay. All right, so here we are. Now it's just execution of the math. And let's go through this at least once. Okay. We'll see here that this is rho R to the fourth and 4, evaluated between 0 and A on H times X. Still have to do our integration on theta and X. Okay, so I can sort of plug things in here for my R variable, given the bounds here. And if I want to simplify my life, I'll pull out rho on 4. And on the inside here, I'll have A to the fourth, X to the fourth, on H to the fourth. Still d theta dx. Now I'm working my way again on the interior integral. And we'll notice here that our integrand does not have any dependence on the variable theta. So X does not depend on theta in any way. And all those other variables in there are just constants. A and H and rho are all just constant values. So we're ready to just apply what is the first fundamental law of calculus and just say that directly we may write from 0 to H 2 pi rho on 4. Purposefully not simplifying this so you sort of understand what's happening. Okay. I'm going to pull out constants here to make my life a little easier. Here, let's go. Pi rho A to the fourth on 2 H to the fourth. None of those are dependent on X. Okay. All right, after integration, we're going to have X to the fifth on 5. I'll just plug in for H directly. H to the fifth, 5. You can simplify or pull out some H's here. And you'll be left with pi rho a to the fourth h all on 10. Okay. So this would be an appropriate answer, I guess you could say. We do have units of mass times length squared, though it doesn't really look like it. Remember, your density is, kilograms per meter cubed times meters to the fifth would be something like kilograms times meter squared. But this is where the trick of substituting back for the mass will come into play. All right, so let's remember. Way back from the beginning of this, that your mass is 1/3 pi rho a squared h. Okay. And so you can express this here by sort of plugging a mass unit in there and rearranging constants a little bit to write your mass moment of inertia in terms of mass times a length squared much more clearly to identify, where m is the mass of the object. So if we did that, you would end up with here 3ma squared on 10. And if you go to any standard table of mass moments of inertia of right cones, you will see this value. And now it's not a mystery where it comes from, hopefully. Okay. I think we'll take, let's take 7 minutes here. Come back at, see on the clock down here, 4:43. Come back at 4:50. See if you can set up IY. See if you can do it. If you want a challenge on your break. It's a toughie. I'll be back. Don't mind me, I'm just drawing stuff. Ooh, this is a complicated one. All right, 450, let's get back into it. I'm just going to forewarn you about this upcoming portion. I will not ask you anything nearly this difficult on the test. All right. This particular integral, very difficult to set up and pretty difficult even to evaluate. But I think it's good to get some sort of mathematical hair on your engineering chests, and I think we should go through it. So we'll remember that our mass moment of inertia about the y-axis, here if we think about any particular element that exists on this particular object, let's say we're up here with this differential mass dm, then we're interested in the distance that this particular object is away from the y-axis. And remember here, we call this like the distance dy, okay? And if we know or happen to know the xz coordinate of that particular differential mass, well, then the mass moment of inertia of this particular object would look something like the distance squared times dm, where here the x squared plus z squared would be that distance squared multiplied by the differential mass, okay? So if you happen to know what the xz coordinate is, meaning think about projecting this down to like the xz plane. If you happen to know what that xz coordinate is, you know what the distance that that particular differential mass is away from that y-axis, all right? So this is a nice form to work with. The problem here is that your z coordinate, which is, you know, an important coordinate for this particular integration, is going to change as you sweep your mass around the angle theta, okay? So I think you can pretty easily understand that if I have a differential mass that exists at this particular location, all right, my z coordinate is, you know, whatever it is. But if I have a differential mass over, let's say, farther on this particular object, and I want to project its location away from the y-axis, here, this is a new distance away from the y-axis, dy, and I project it down here, I have a different z coordinate for that particular differential mass. And so it becomes tricky here now in that when we're defining the location of our particular masses, not only is it dependent on the variable r, which is the distance away from the center of the cone, but it also depends on sort of the angle that we're sweeping through, which is this theta direction as we move our differential element through the integration in the theta direction. So this is also going to become an important factor when we're looking at our integration for this particular object. This wasn't as big of a deal when we were looking at integrating about or doing our area moment, mass moment of inertia about the x-axis, because our pieces were always sort of had the same sort of distance away from the x-axis. Our distance away from x did not depend on the variable theta which we swept through. It always maintained a constant radial distance away from the x-axis, and so that made things relatively easy. But when we go to the integration for the mass moment of inertia about y, things get more complicated. And then we sort of have to define each one of these particular elements using some trigonometry here, where this z coordinate is going to be something like r times the sine of theta, right? Where theta is the angle that's made here. A little bit complicated. But let's move forward. Okay. Wish I could blow this up a little bit more. Maybe I should have drawn this picture a little bit bigger, but this here is like our radius r. And so the z dimension, which becomes important in our calculation of the mass moment of inertia of y, it can either be sine or cosine. It's, since we're doing a 360-degree revolution, it's kind of irrelevant. But it's going to be the sine of the angle theta. If you want this to be your angle theta, that's also perfectly fine. Okay, so that's the general idea. So setting this up properly, you would have something like the mass moment of inertia is the integral on the mass of x squared plus z squared dm. And here with our techniques that we just discussed, we're going to have something like still x squared. The x squared is still going to remain. But now we're going to write the z component, which is the z distance away from the y-axis, is going to be r squared sine squared theta. And then my volumetric component is going to be rho dr d theta dx. And this is your sort of setup here. Where on r, we're again going from 0 to our boundary ax on h. It's the function that defines where the radius of the cone is. On theta, we're again going from 0 to 2 pi. And x, we're going from 0 to h. So this is the general setup for the mass moment of inertia about the y-axis. Pretty complicated. I won't ask anything that's tough on the test. This is like insane level, but I think it's good to sometimes dive into some deep math. It's funny, I've had a student in like 5 or 6 classes now, and he brought me a little Christmas present this year, and it was this pair of sweatpants that had a bunch of like math formulas on it. And he said, you can use these now as your math pants. So when I say, I hope you're wearing your math pants today because this stuff's hard, I actually have math pants. Maybe I should have worn them. So this is the general setup. We won't go through the whole integration. This is on Canvas if you want to take a look. But I'll just cut to the chase and say that if you look up what the area or mass moment of inertia of this particular object will be, it's something like 3/5 m times h squared plus 1/4 a squared. If you want some triple integration practice, be my guest. Who's the Disney character in the Beauty and the Beast movie that sings "Be my guest"? What's his name? The candle. Lumiere. Yes, thank you. Did you say Moana? Moana. Okay. No, Lumiere. Lumiere or Lumiere? Is there that extra syllable in there? Okay. So if you want to do some integration, be my guest. Put your skills to the test. All right, so there you go. There's some cylindrical component triple integrals for mass moments of inertia. Complicated, but you can do it. Don't be afraid of math. All right, so here we go now with some additional material about mass moments of inertia. And a term that you'll commonly hear, not only for mass moments of inertia, but area moments of inertia, and we talked about this a little bit already, is this term that's called the radius of gyration. Okay. And the radius of gyration is often a value that's given for materials that are fabricated in the real world as a stand-in for that material's mass moments of inertia. And you'll see why in just a second. But let's consider a rigid body of mass m with mass moment of inertia about an axis of capital I. All right, so the picture that you want to have in your head, here's some axis that exists. Here's some body that we have, some body that I used to know. It's got some mass m. And if we're spinning it around this particular axis, then we'll say that it has some mass moment of inertia I. All right, let's say that that is the case. What the radius of gyration is, it's a stand-in to tell us what the mass moment of inertia is by saying, if we concentrated all of the mass of that body into one particle, how far away from this axis would we have to place that particle so that it would have the same mass moment of inertia as the full body? So let me put that into words. If we could concentrate all of the mass of the body into a particle, I'll say how far away to give same mass moment of inertia. That is the question. Okay, so pictorially, what I mean by that is we've got this body that has some mass up there that's rotating about that particular axis. But let's say we had some superpower that allowed us to concentrate all of that mass into one particular point. And I placed that point at some particular location. And that particular particle has the same mass as that particular body, the mass m. The question is, how far away do I have to place this particular mass from that axis to get the same mass moment of inertia that I get with this full body? So a situation where the mass moments of inertia of these two particular systems is equal. And typically we would label the distance that this particle mass has to be away from this axis with the variable little k. It's just by convention. Convention with a C, not with a K. Okay. Okay, so that distance is the radius of gyration. All right. So if the mass of your body is I, and we know that for a particle, the mass moment of inertia is equal to the distance that that particle is away squared multiplied by the mass. So the mass moment of inertia of a particular particle is the mass of that particle multiplied by its distance squared. Then we can just rearrange and say that radius of gyration of any particular object is equal to the mass moment of inertia, I, divided by the mass of that particular object. All right, this has units of length. And typically this would be specified as something like kx, ky, kz, right? Radius of gyration about x, y, and z axes. All right. This leads me into the next topic, which is the parallel axis theorem for mass moment of inertia. Okay, we already did sort of the parallel axis theorem for area moments of inertia, and you'll see a lot of analogies here, a lot of parallels between the two. Oh man, that was terrible. Come on, I didn't even get one little chuckle out of that. Come on, are you guys even awake? All right. So parallel axis theorem for mass moment of inertia. You already kind of understand maybe what this is or where I'm going with this. But the idea is if you have some composite body that is made up of many bodies that you happen to know what the mass moment of inertia of those individual bodies are, and those individual bodies make up some composite body, and you want to know the total mass moment of inertia of that composite body about some axis, you can utilize the parallel axis theorem to relate mass moments of inertia of objects that you know in that composite body to mass moment of inertia of the total object, which is something you might want to know. So let's work our way through that and see that derivation. So let's consider. We're going to have a body of mass m. With known mass moments of inertia in rectangular coordinates. Let's say rectangular centroidal coordinates. Okay, and we'll assign these as, let's say, I bar x, I bar y, and I bar z. These are the mass moments of inertia of our particular mechanics potato about centroidal rectangular coordinates. So let's put a picture to this. Okay, here's your mechanics potato. It's got a centroid there at the middle, and let's say that's at point C. And we've got a coordinate system here coming off of this. It's like X, Y, and Z. And since these are centroidal, let's give it some primes so we know. We're going to assume we know what the mass of this object is. we're going to assume that we know what the mass moments of inertia of this object is about those particular axes, the x prime, y prime, z prime axes. All right. So this is what we know. Now let's say that the mass moment of inertia about another arbitrary axis, or in this case, coordinate system, centered at some point O. Well, what do I mean by that? All right, well, there's some other coordinate system that exists out here in space. Let's call it X, Y, Z. All right, maybe I should try to draw it so that it's the same general feel. Exists out in space there, and I want to know what's the mass moment of inertia of this object about the x, y, and the z axes, given what I know about the mass moment of inertia about the centroidal axes, x prime, y prime, z prime. All right. So let's give some additional information here. We'll say point C is located at the point x bar, y bar, z bar in the O coordinate system. All right, so here's point O. So that's just, we know where the centroid is of this particular guy. It's located in the XYZ coordinate system at the position x bar, y bar, z bar. Okay, so what that means is, all right, I know where in space this particular point exists, x bar, y bar, z bar. Okay. And let's say that there is a differential element that exists in this particular guy. And we'll say that that differential element dm exists at location x prime, y prime, z prime in the C coordinate system. Okay. So then with that idea, my differential mass in the O coordinate system, which is the coordinate system that's sort of arbitrary in space, it's going to be at the centroidal location, x, plus whatever distance I am in the C coordinate system. So let's just, pick an axis and see what happens. All right, so let's just maybe pick the x-axis. So examine the mass moment of inertia about the x-axis, which is this axis that exists in some arbitrary location in space. All right. We know that this looks something like y squared plus z squared dm. but I want to write the location of the differential mass, not in terms of y and z, but in terms of things that I know, which is in terms of y bar y prime, z bar z prime. So this is the integral of y bar plus y prime squared plus z bar plus z prime squared, integrated over the mass. All right. Let's do some foiling, rearranging of our integral. Do they still teach like the FOIL method? You guys don't know the FOIL method? Are you serious? Do you guys know the FOIL method? Okay, some of you know it. Mario, you never heard the FOIL method? First, outer, inner, last? That's how you operate on binomials? Wow. I mean, you don't have to like learn that. It's just like a technique for expanding a binomial. But okay. We're going to expand these binomials. We'll speak in Mario language. We're going to expand these binomials, and that's actually the proper math language. And then rearrange the integrals. And if you do that, you'll see the following. Be the integral y prime squared plus z prime squared dm plus some weird terms here. The integral of 2 y bar y prime. All right, that's coming from sort of the second term in this binomial here. Plus integral in the mass of 2 times z bar z prime. Now you see why I put a dash through my z's, because my 2's look like z's. I'll put you to sleep. All right. Plus the last little bit here. Left over from my foiling. All right, so this is just an expansion of that particular integral up there. Now let's see if we can do some identification of these things. All right. Who wants to identify this guy? Who can do it? I bar. Very good. So this is the mass moment of inertia of this particular guy about the x-axis in its centroidal sense. So y prime squared plus z prime squared differentiated over the mass. If we go back up here, that is just our definition for the mass moment of inertia of this particular object about its centroidal x prime axis. Okay, sweet. That's our centroidal mass moment of inertia. All right. We'll go to these two terms next. We'll say the same thing about both of them. These two terms here are both 0. And the reason why is, again, we have some integration of odd functions over equally spaced bounds. So I'll say these are 0. And it's integration of odd function over mirrored bounds. All right. Y bar is a constant value. Z bar is a constant value. They get pulled out, right? So you have an odd function when you only have one variable dependence, single variable dependence on the integrand there. And sort of because of the way that this integration is going to go, since we're located at the centroid with our particular x prime, y prime, z prime axes, we have mirrored bounds in either direction. We're integrating an odd function over mirrored bounds. These are going to be 0. A little bit complicated to maybe wrap your head around that. You guys talk about odd and even functions in calculus? Yes? No? Not really? No? Oh, okay.
Yeah.
Yeah, okay, well, someone said yes in my ear, so quick aside. Um, you don't have to write this down, but teaching moment. So an odd function is one that's more or less the same on the y-axis, but negatively charged, I guess if you want to say that. So this would be like an example of an odd function. So if I were to integrate this over mirrored bounds, I'd have the same amount of material below and above like the y-axis, so it would all cancel out. That's what I mean by integration of a odd function over mirrored bounds. Another odd function might be like x cubed, which looks something like this, right? If I were to integrate that particular function over mirrored bounds, you would also equate to 0. That's the idea of integration of a mirrored function over, or of an odd function over mirrored bounds. Okay, so that's why those go to 0. Lastly, here. The values of y bar and z bar do not change as I move my differential mass around. Okay, what do I mean by that? These values here, y bar and z bar, this is like the distance away between O and C. Those coordinate systems are not, those coordinate systems are fixed. All right, the distance from O to C is the centroidal distance that this object has away from O. So those values are fixed. X prime, y, x bar, y bar, and z bar. Those are fixed in space. So I can move my differential mass around here all I want and integrate over this particular body. That doesn't change anything related to like the distances here between O and C. All right, those axes aren't moving in any way. They're sort of fixed in space, both O and C. And so regardless of if I'm integrating over this particular body, it doesn't really matter, right? These y bar and the z bar, it's fixed in space, all right? These are constants that we can pull out of the integral. And so this here is just the distance that exists between the x-axis of coordinate system O and the x-axis of coordinate system C. These are constants. And we would just be left with the integral on the mass. So what you end up with here is something like the mass times y bar squared plus z bar squared. All right. So all this to say that the mass moment of inertia about the arbitrary x-axis is the mass moment of inertia of the object about its own centroidal axis, here the centroidal x-axis, plus the mass of that object multiplied by these centroidal distances, y bar squared plus z bar squared. Okay. This is a sort of loose definition, and we're going to refine this a little bit in just a second. So here we'll note that y bar squared plus z bar squared is the distance from what is the x-axis to the x prime axis. Okay. So this y bar squared plus z bar squared. If I could draw well, I don't want to try to draw this well, but here, that is, if we had like, this was y bar and this was z bar, then this here we could define as like dx, which is the distance between x and x prime, right? So y bar squared plus z bar squared is the distance from the x-axis to x prime axis squared. So more often, you'll see this as something like ix is I bar x plus md squared. This is probably the most common form, where Ix is the mass moment of inertia about an arbitrary axis. I bar x is the mass moment of inertia of the object about its centroidal x-axis. M is mass of object. So total mass. And d is distance, let's say parallel distance, between centroidal axis and axis of interest. All right, there you go. So that's kind of like the most general form that you could have. You could repeat this for, you know, y and z axes as well. This is one form. Another form. Or if you want to be most general, you would just simply see this as. And this is what you're going to see in pretty much every textbook, but really it's important to understand what the D is here. The D is the parallel distance between axes of interest. It's really what it boils down to. In rectangular components, that's like a x squared plus y squared term, something along those lines. And you'll find listing after listing. Someone's calling me. Why is someone calling me? Don't they know I'm in class? Oh. So you go to any table with mass moment of inertia, area moment of inertia, you'll find listed common area moments of inertia, common mass moments of inertia. And so if you have an object that is made up of common objects that you might find in a mass moment of inertia table, well, you can use the values from the table and the parallel axis theorem to give you what is the sort of composite mass moment of inertia of that particular object. So it's sort of a very, very powerful tool. You saw this with your most recent homework with area moment of inertia. You'll see it again on your upcoming homework for mass moment of inertia, and that this can be pretty powerful and used pretty often. So you can go to your textbook and you'll see charts that look something like this that tell you what is the mass moment of inertia of these three-dimensional objects about their centroidal axes. So you see most of them here listed about their centroidal axes. This circular cone here, it's not necessarily centroidal, but you know, it's giving you information that you could use and then transform from there. So that's the idea. So if you have information about the composition of the body and the composition of your composite body is made up of shapes that you can find easily in a chart, you're not going to have to do all your crazy integration. No triple integrals required if you can just like use what's already in these tables, right? That's nice. Okay. So an example might be something that looks like this. You've got this right circular cone, and I already kind of told you that the mass moment of inertia of this particular cone about the y-axis is 3/5 m times the quantity h squared plus 1/4 a squared. And so if the centroid of this cone is located along the x-axis at a distance of 3/4 h from the xz plane, so it's kind of marked there in the picture for you to see, can you calculate the mass moment of inertia of this particular object about its centroidal y-axis, given what you know about the mass moment of inertia of this object about that arbitrary y-axis in space at the cone's tip? I'll give you a second with that if you want to take a look, and then we'll power through it, and then we'll get you out of here today. Okay. I'm going to copy this over, and we'll go through it. I like to use the double prime here. I'm just going to call this IY bar because this is a centroidal axis. Okay, so we'll use parallel axis theorem. And remember that the general form here is that the mass moment of inertia about an arbitrary axis is the mass moment of inertia about a centroidal axis plus the mass of that object times the parallel distance squared between those two axes. Okay. So be careful in this particular situation that you don't confuse the left-hand side I and the right-hand side I here, okay? We're looking for this guy, all right? This is our unknown, okay? We're looking for the centroidal mass moment of inertia. We have this. We're going to assume we have mass, and our D here is 3/4 h, right? A parallel distance between the two axes of interest. Okay, so let's roll with this. So here, is my general formula. And remember that I'm actually solving for my centroidal area moment of inertia. So I have to subtract the contribution from relocating this away from the centroid. Okay, so we saw that this was 3/5 m times h squared plus 1/4 a squared. Minus m times my distance between my y-axis and my centroidal y-axis is the centroidal length 3/4 h squared. All right, so we can do some expansion here. 3m h squared on 5 plus 3 a squared m on 20 minus 3 h squared, not 3, 9 h squared m on 16. All right, so we got a lot of weird denominators going on here. Common denominator of all these guys is going to be 80. So let's just write that. 80 by 5 is 20. So here we have 80 by 5 is not 20, it's 18. So here we'd have 48 mh squared over 80 plus 12 a squared m on 80 minus, here is where the 5 comes in, 45 h squared m on 80. Okay. I've got some common terms here and here. They both contain mh squared. I also have an m that's kind of worked its way there as well. But we can sort of factor some things out and make our lives a little cleaner by just sort of whittling these two terms down together, combining them. So here you're going to have something like 12 a squared m over 80. Here, plus 48 minus 45, 3 h squared m over 80. All right. Can take some constants out of here. Find that your centroidal mass moment of inertia about here, let's be clear, the y-axis, kind of been sloppy about dropping that. After some factoring, 3m on 20 times a squared plus h squared on 4. And if you go to tables, textbooks, etc., this is what you'll find for the centroidal mass moment of inertia of a right cone with those particular dimensions. How are we doing? Good? Happy? Awake? Looking at you. Okay, that's gonna be it for today. I'm gonna need a couple minutes on Thursday to finish up mass moment of inertia, but then we'll start in on motion. Yes, finally. Kinematics on Thursday. I will see you then. Count every vote. Okay, that's nice. Nice. Did you volunteer at the polling place? I was gonna say that must have been a zoo, man. My brother worked as a poll worker in Cincinnati area. He lives in one of the suburbs, so it wasn't as bad, but he said it was pretty nuts. Yeah.